Screen recording starting. Okay, so it is recording. It says it's recording. Let's keep going. All right, guys. Equilibrium problem. First example we have. Let's just take a very simple example. We'll take a horizontal line right there, and we're going to put a box on it, or like a crate on this particular spot. And this problem like this might read, a 20 Newton crate is on a horizontal surface. What is the normal force on the crate? Okay, tapping things. Okay, so a 20 Newton crate's on a horizontal surface. What's the normal force on the crate? Now there's two objects in the picture. There's a crate and the floor is shown. You're going to draw a free body diagram based solely on the crate itself. So if this is the crate, now there's some minutia here when I just say 20 Newton crate. When I say the crate is 20 newtons, that refers to the weight of the crate. This capital N is something called a newton. This is a unit of force. That's a unit of force. It's equal to something, but we don't know what it's equal to yet because we're not doing the lab yet. But it is the unit of force that is used in this particular part. Now, that unit of force is the weight, and it's going to be labeled downward. So that's 20 newtons. Now, since it's equilibrium, the sum of the forces acting on it must be indicated with arrows. And if I add them tip to tail, they must add up to, or if I put them tip to tail, they must start in the same spot that they end. So if I draw an arrow upward representing the normal force, it's like the question is, how big do you want to do it? Do you want it really small, or do you want it really big? Well, you want it around the same size as the other one. Okay, because these forces must balance. And we're going to call this normal force. Now I know what you're saying. What is the normal force on the crate if they balance? And you're saying it's 20 newtons. Am I right? But how do we express that in terms of the equations that we're given? So equilibrium has a very simple equation. Looks like this. The net force. Okay, what is that symbol? Sigma. Okay, is that like hurting you right now? Is that giving 71 problems on a statistics paper yesterday that you had to turn in? Was it that many? 79? Oh, sorry. Disrespect there on it. 79. Did you have any sigmas on that? Yeah. So that means the sum of everything, right? You're totaling it up. Now, in this case, we're going to specify what it is. If I drew a coordinate axis on this thing, like here, boom, boom, this is the x direction, this is the y direction on this axis. And so, just kind of laid that out in red. So you got that x and y direction. This is in the y direction. So the sum of forces in the y direction equals 0. That's equilibrium. Okay. Now, what are those forces? I'm going to do a run-on equation, and you're going to see this a lot in your textbook. That's why I do it. Plus, it saves a little paper if you do some of this. Okay, so that sum of forces, well, since it's a coordinate axis, you still have a convention. So we'll say positive is upward here. And so that sum of forces is going to be my normal force, which is positive. Now that 20 newtons is going down. What should be in front of that 20 newtons? Negative. Minus 20 newtons. Now if I look at this part of the equation right here, I could take that 20 newtons, add it to the other side. So I get 20 newtons equals the normal force. And that is how you kind of lay out, well, what normal force is 20 newtons. And step it by the equation right there. So that's going to be your bare basic type question there. Now, it can complicate a little bit if we add two objects. And let's do a similar thing. But let's do it in the other direction, just so we see a different direction. Let's draw a big, large crate type thing. And we'll put some forces on this. We'll put a person pushing this thing here. And we'll put another person pushing this thing there. And we'll put a little baby person pushing that thing there. Okay, so now this is at equilibrium. Okay, a large crate is at rest on a frictionless surface being pushed by 3 people. Okay. Okay. It's pushed to the right at 200 newtons, to the left by a big guy at 180 newtons, and to the left by a baby guy 2. Okay, what is the force from the baby guy? Okay, so what's the force that little baby guy pushes compared to the other ones? Now I know what you're thinking, and you really want to do it. You just want to write 20 newtons. Am I right? You want to do it, and I wrote it like that so you could see it's 20 newtons, but how do we show it in physics? So the sum of our forces, well, let's draw a free body diagram first. Okay, free body diagram, I'll do it in blue. We'll emphasize it. Well, it doesn't have to be right there. Okay, so this guy is pushing it this way at 200 newtons. You got the big guy on the left side is pushing it this way at 180 newtons. And we can thicken up the circle right here because we add a second guy pushing it left. And this is the force from the baby guy. We'll just call it B. Okay, that force B, it is a force. Capital letters note forces. If you want a vector hat over it, sometimes you'll see a little vector hat over that particular thing. See, it's a little vector hat. Boom. Now, all right. Now, what's really cool is those 3 guys are all following the Spirit Day-to-Day, black and white. Like some of you are not purple wearer. Oh my gosh. Now, all right. So the sum of my forces in the x direction equals 0. Ooh, it's x now. But positive, we'll call it that way. So you always got to understand that going towards the right, we can make it positive. Going towards the left, we have to make it negative. It doesn't matter if it's really positive or negative. You can choose negative going right, but that would be weird. As long as it's consistent throughout the whole problem. That's a convention. All right, so I'm going to call that 200 newtons minus 180 newtons minus the force from the baby guy. Now I'm going to move my B to the other side. That force from the baby guy is 200 newtons minus 180 newtons. And the force on that baby guy is 20 newtons. Boom, there it is. So there it is, equilibrium. Simple enough. It gets a little bit more difficult as we go along. Okay, so that's your basic force in the x direction, force in the y direction. What about forces on a surface, like a slanted one? Let's do forces on a slanted surface. There's a slanted surface. And we'll call that a 15-degree angle from horizontal. Okay, so a dot, because I'm going to draw a dot. I'm going to represent the free body diagram there. A dot, well, let's give it some mass here, or some weight. How big should that dot be? 50. A 50 Newton dot, what did I do there? Let's move that around. Slipping around, 50 Newton dot. Look at that. That probably took more effort. A 50 Newton dot is at rest on a 15-degree slope from horizontal. Okay, what is the friction force and the normal force? So what's the friction force and what's the normal force acting on this? Okay. Are you ready? Get rid of that. What does a free body diagram look like on this thing? Well, I'm going to draw this downward. Okay, so this is my 50 Newton force. Okay, that's my weight going down. Actually, the force due to gravity, we'll call it. Now, it's pushing against the slope. Do you guys remember which direction normal force goes? Perpendicular to the slope. How big should it be? Well, if I start from the tip of the other one, going up this way, it's going to bring it right to there on the slope. So I can move that. Oops, what I do? This way. So it's about that large. And you'll get used to drawing these. It's probably the first one you've drawn. Now, if I add all three of these, it's at rest on the hill, right? So I'm going to drop this back down. Watch out. Put this back down here. There's that normal force vector. Do those look like they're in equilibrium, those two vectors alone? You need a third one. You need something that's going to bring it back to the center, like coming off this way, about that large. Darn, I can't get it straight. Well, that's as straight as I'm getting it. It's a little crooked. The autocorrect made it crooked. Okay, so it's about that large, but I'm going to put this vector like right there. Give it a tip. And I'm going to put this vector, oops, what happened there? I'm going to move this vector back to where it should be. So those are the three vectors that are going to add up and bring me back to my starting point. Okay, this is the normal force. And what's keeping it on the slope from sliding down, that extra dot, is friction. I want to call it the force from friction. I don't know either of those. Okay, and I got to figure it out through this particular problem. But the problem I have is those vectors are not all in the x direction and all in the y direction. Right? I have one in the y direction going down, and I have those two are kind of slanted. But I want to do something creative. Now, this is when we work on slopes, you got to be creative like this. I'm going to draw an axis. Okay, here's my axis right here. There's my xy axis. Now, you know what I'm going to do with this xy axis? I'm going to take it and I'm going to twist it. Boom. So I'm going to take my xy axis and put it right on the slope to where my x is going down the slope and my y is like straight up from the slope in that normal direction. And this is going to be helpful when things are actually sliding. This is not sliding right now, but when they're actually sliding, what's going to happen is it's going to move along the x-axis is much easier. All right? So we're going to twist our x-axis. Now, the friction vector and the normal force vector are on the x and y axis. The only problem is that gravitational force vector is not. And we're going to resolve that gravitational force vector. Now, if you look at it, okay, you look at this right here. This makes like a triangle at the bottom. And I got my 15 degrees in this bottom corner from that. And I got, it's a right triangle. Look at that. Right triangle. That makes this side 75 degrees. And that makes this side over here, because they're complementary, 15 degrees. So this triangle right here is that has a 15-degree angle there, which makes the vector going down this way. When I resolve that x vector, this is going to be 50 newtons times the sine of 15 of that angle, because that's the opposite side. It's going to make this vector going down this way 15 newtons times the cosine of 15. I did that last time too. 50 newtons, my bad. 50 newtons cosine 15. So you got 50 sine 15 and 50 cos 15. And I've resolved that gravitational force vector. Make it nice and bold. And now you can write your particular equations. Okay, so sum of forces in the x direction equals 0. And in the x direction, I'm going to have 50 newtons sine 15 minus the friction vector. And the force of friction is 50 newtons sine 15. And that means my force of friction is 12.9 newtons. And in the y direction, the sum of, it's a terrible sigma, whoops. Sum of forces in the y direction is 0. And you can see in the y direction that I have, that equals my normal force minus 50 newtons cosine 15. Move it up a little. So my normal force is equal to 50 newtons cosine of 15, and that equals 48.3 newtons. So breaking it up, doing each of those. All right, so that's forces on a slope equilibrium. The takeaway here is set your axis parallel to the slope, your x-axis parallel to the slope, resolve the gravitational force vector, and then you have your x and y components where you can set equal to one another at equilibrium. Not too tough, right? All right, now we jump to maximum strength. Are you ready for maximum strength? I have an actual picture of maximum strength right here. That's where that stoplight comes from. So, the classic physics problem, the stoplight problem, and it's in the textbook. It's an example from the textbook. You at home the home audience can see the textbook thing, but I'll draw it right here. So, don't know why a stoplight's hung like this, but you hang a stoplight from these positions. And this is the stoplight itself. We have the red light. We have the yellow light. Actually, it's more like orange light. We have the green light. Although nowadays the stoplights, when they replace the new ones, the yellow light's actually looking much yellower. Okay? The lights of old look very orange, don't they? I want you to think about that one. This is 37 degrees. This is 53 degrees hanging. That's like where they're all kind of come together. And the stoplight is a 100 Newton stoplight. It has a weight of 100 Newtons and it's pulling down. The question in the stoplight problem. You get the 100 Newton stoplight hangs, 100 Newton stoplight hangs. Okay, it's at equilibrium. I'm just going to call it that. It's attached via the picture. Check out the picture. Those two cables are making those angles of 37 and 53 from the horizontal. Find the tension in each of the three cables. You got to find the tension in all three cables. Now, we're going to do that bottom one right away. This bottom cable right here, this bottom one, well, you got the stoplight. If I do the force on the stoplight, okay, that's the stoplight Stoplight gravitational force is 100 newtons. What's holding up the stoplight? Well, this is going to be, let's label it in the picture here. T1, this is T2, this is T3. So what's holding it up is this T3, this tension 3, and those balance. Sum of forces in the y direction equals 0, and that means that's going to be T3 minus 100, and so T3 equals 100 newtons. Put a unit on that. So we got T3 at 100 newtons. There we go. We're good to go. Now, I'm going to redraw the free body diagram as I move it down, all the way down, just to make it clean and nice, and I'm going to do some problems from it. Okay, so this is going to be our T2. This is going to be our T1. And this is going to be, well, we figured it out already. That's 100 newtons. Pulling down from the knot that in the middle, that little dot. And we have some measurements from the horizontal. I won't draw those angles from the top. I'll draw their alternate interior angles. This is going to be 53 degrees, and this is 37 degrees. Okay, so normal convention, y is up this way, y is straight up, x is that way, and that's the positive direction of each one of those. So we have to resolve these vectors. Those crooked vectors, always resolve them. So if I want to figure out the horizontal vectors from each of these, and those angles are adjacent, right? So this is going to be T1 cosine 37, and this is T2 cosine 53. Now the vertical vectors, this vertical one here, that's T2 sine of 53. And the one here, put it right next to it, squeeze it right there, that's T1, whoops, do right, sine 37. Are we okay with resolving the vectors? Is that a headache for anybody? I know I'm going pretty fast. All right. But we'll do some examples, hopefully. Now, we got to write our equations. So we have two equations to write, and we'll start with this one. The sum of forces in the x direction has to equal 0. Now, in the x direction, we have T2 cosine 53, that's to the right, positive, minus T1 cosine 37. And it's minus because it's going towards the left side. Now I'm going to leave a space. I'm going to leave a big space right here, and you'll see why. Okay, sum of forces in my y direction equals 0. Now going upwards, we have T1 sine of 37 plus T2 sine of 53 minus 100 newtons. All right. Now I left that space. Hopefully you didn't write space like I did, because, oops, what did I just do? Eraser. Okay, because we're going to be solving the system. If you look at this, these equations right here, this equation 0 equals that and 0 equals this, there are two unknown variables. So we're going to solve the system by substitution. Very simple way to solve a system. So we're going to take that first equation right here, and we're going to solve it. Let's just move some numbers over. Okay, so I get T1 cosine 37 equals T2 cosine 53. So I move the T1 cos 37 to the left side. Now I'm going to solve it for T1. I'm going to say T1 equals T2 cosine 53 divided by cosine 37. That means my T1 is equal to, and do I solve it? 0.75. I want to get some bigger digits on that. Keep 1/10. The book keeps 1/10 on it, so that's going to be 53 cosine divided by 37 cosine. We'll call it 4. That's going to be T2. All right. So there's an equation. I should kind of outline it in red. So 7, 5, 4. Boom. It's in red right there. T1. That's like our equation 1, and we can shove it into this thing. Now, so I'm going to take that equation. I've solved it down, and I'm going to put this T1 in for right there, in the T1 on the other equation. And so it's going to look like this. I'll move it down. 0.754 T2 sine 37 plus T2 sine 53 equals 100 newtons. And we crunch it. We go 0.754 times 37 sine. That's going to be 0.454 T2. And this one here is 53 sine. Okay. Plus 0.799 T2 equals 100 newtons. Plus 0.454 equals. So 1.25 T2 equals 100 newtons. And T2 equals 79.8 newtons. There we go. Now, I'm going to take that first equation right there, move it down here, and find my T1. T1 equals 0.754 times 79.8 newtons. And my T1 equals times, let's see, 0.754 is 60.2 newtons. Terrible N. That's an N. Okay, so my T2 is 79.8, my T1 is 60.2. I think I kept an extra digit. So your textbook answer is like 79.9 and 60.1. And there we go. Got my tensions. And of course, T3 was 100 newtons. I solved the problem. What do you guys think? This is as hard as equilibrium really gets. The equilibrium problem. That's like maximum strength right there. All right. So let's see.